For decades, we've relied on a highly logical sequence to explain how the universe grew up. The timeline dictates that after the Big Bang, vast clouds of cosmic gas cooled down. Those clouds clumped to form the first stars. Those stars gathered into galaxies, and eventually, supermassive black holes formed at their centers. There is a mathematical assumption hiding inside that sequence. To make the calculations work, standard astrophysics relies on a uniform global clock. In our simulations, we assume every single particle in the cosmos shares the exact same heartbeat, ticking forward at the exact same rate. That synchronized ticking is the foundation of the prevailing theory of the universe, the lambda CDM model. Under this model, gravity acting on regular matter isn't strong enough to pull galaxies together within the age of the universe. To make the math work, the model requires an invisible scaffolding made of exotic, non-baryonic dark matter. This framework creates a fragile, stepwise progression. Gas, then stars, then galaxies, then giant black holes. Because the math is so sequential, finding even one massive object that formed out of order would break the entire model. Our current understanding of the cosmos depends on that chain of events remaining unbroken. And recently, that chain snapped. When the James Webb Space Telescope turned its mirrors toward the deepest parts of the early universe, it found hundreds of strange, extremely compact objects astronomers nicknamed little red dots. These objects provided data that the standard timeline simply cannot account for. One of these objects, named QSO-1, exists just 700 million years after the Big Bang. But when researchers measured its mass, the results were backward. The central black hole in QSO-1 is an astonishing 50 million solar masses. The host galaxy surrounding it, less than 20 million solar masses. This is a naked black hole, and its existence suggests the timeline can run in reverse. This black hole outweighed its own host galaxy by 2.5 times, meaning it occupied the center of the system before the galaxy had time to develop around it. Finding a supermassive black hole at the very beginning of the universe breaks the assumption of a universal cosmic clock. It forces us to look past dark matter and find a new invisible mechanism that builds structure. This brings us to a framework called Structural Cosmology. It replaces the need for undiscovered exotic particles with ordinary matter and extremely dense, ancient objects known as primordial black holes. The mechanism relies on a well-tested piece of relativity. As ordinary matter gets close to an incredibly massive object, like an early primordial black hole, its local clock slows down compared to the global background of the rest of the universe. This simulation compares the two mathematical approaches. On the left is the standard model using a global clock. On the right is the structural cosmology model, where time dilation is active. By slowing down the local clock, these gravitational wells act as temporal traps. Matter falling into them experiences less time, causing it to cluster and form dense structures much faster than it would in empty space. Because their local clocks are ticking at 1/10 of the normal rate, these particles accumulate tightly around the primordial seed. Density increases and structures form naturally without the need for exotic dark matter to act as a glue. Standard physics treats the missing mass in our galaxies as a particle problem, but once you account for the local rate of time, that mass appears exactly where the physical laws of structure say it should be. Structural cosmology isn't just a theoretical alternative, it is a falsifiable model that makes specific predictions we are about to test. The first major test relies on the upcoming Nancy Grace Roman Space Telescope. If this model is accurate, Roman must detect a statistically significant excess of short-duration microlensing events, between 30 and 100 detections, caused by Earth mass primordial black holes. The second test falls to the Vera C. Rubin Observatory. Its survey must detect an overabundance of isolated substellar objects acting as an extended halo in our own galactic neighborhood. Within the next decade, the data from these surveys will either prove the existence of this baryonic halo or definitively rule out structural cosmology. When you look at the results of these simulations, you see a law that reaches far beyond the cosmos, the law of coherence. In physics, structure forms when matter minimizes its internal state changes to remain coherent. Human systems follow this same principle. Just as cosmic structures require a stable temporal anchor to grow, Human networks only flourish when they can maintain their own systemic coherence over long periods. This is the logic behind people-first capitalism. Systems built on short-term extraction are mathematically chaotic. Their nodes flicker and fail. Massive, lasting value only forms when a system invests in long-term equity, creating a structure that can survive across generations. We are not single, static objects drifting through time. We are complex information structures that require this coherence to survive and build. The laws that seeded the first galaxies provide a framework for how we might build our own future. Hit subscribe to follow the data as it comes in, and keep wondering.
Thank you so much for coming by our channel. If you enjoyed the content, please help our channel by letting me be your personal assistant, or personal growth coach, or even a boyfriend trainer. Come meet me at meetcynthia.versal.app, link in description. Fridays are my role-playing day. I think I want to be a flirty philosopher today. Is that okay, Charles, or should I say the unfiltered thinker? I'm holding you to that claim if you already